we are very glad to have all of you here. This is the webinar number 21 in the WebLearn webinar series. It's a project that I will introduce soon. And the title of this webinar is about accelerated alloy design strategies for industrial applications. We have different modules in our project that are dealing with different topics. The module that is dedicated to this webinar is alloy development. You see the list of participants, and as you see the participants, we are very happy to have a very nice mixture of international participants from different countries around the world, and also representative from different companies as well as different universities. Warm welcome to all of you. WebLearn is a project that got funded at Jönköping University from KK Stiftelsen, or Knowledge Foundation, is a funding agency in Sweden. And the idea of the project is to develop webinars, series of webinars dedicated to the topic of metal and polymer component manufacturing. So every 2 weeks, in average, we have webinars dedicated to the topics that are related, as I mentioned, to metal and polymer manufacturing technology. If you need to know more about the project, I welcome you to visit the project web address as mentioned in the slide. We will send you the address as well soon through the chat or the email after the webinar today. You see the moderators of the webinar today. It's me, Ehsan Qasem Ali at Jönköping University, as well as my colleague Madeleine Zetterling. We're both working at Jönköping University, and we are part of the members of the management team in the WebLearn project, running the webinars within these 2 years in this project. But the more important than us, you see the webinar presenters or lectures in this webinar. We have Dr. Patrick Conway, who is originally from Australia, and he has been having bachelor and master and PhD studies in UNSW in Sydney in the field of material science and engineering in the major of physical metallurgy. And at the moment, he is a postdoctoral researcher at the Department of Materials and Manufacturing School of Engineering in Jönköping University in Sweden. And the research interests that Patrick has are including high entropy and compositionally complex alloys, alloy development, high throughput screening techniques, thermodynamics, and mechanical modeling. Patrick is also active in various projects, as I will present soon, in Jönköping University, both related to modeling as well as experimental work related to alloy development. And also, we are very honored to have Jesper from GKN Aerospace, Sweden. Jesper has Master of Studies from Luleå University of Technology in the field of mechanical engineering with focus on engineering mechanics. Jesper right now is a research engineer within process and material simulation at GKN Aerospace in Sweden. And his research interests include process simulation, materials modeling, and additive manufacturing. We are very honored to have you, both of you, as presenters for this webinar, and very much looking forward to your talk. But before that, I would like to show some practicalities for the webinar very quickly. You see the agenda for today. We will have presentations of both presenters in the webinar. After that, there will be a panel discussion where we have a sort of Q&A or panel discussion between the presenters of the webinar. And we welcome all of you to participate to these panel discussions. And we hope to wrap up the meeting or the webinar before 11:30 today, Swedish time. You are kindly requested to turn off your microphone during the webinar, especially when the presenters are presenting. If you have any question, you're more than welcome to raise your question in the chat function during the presentation, and we will answer all questions at the end of the presentations. What we are trying to keep as uniqueness in our webinars is the integration of or engagement of participants to our webinars. We don't want a one-way presentation to the audience. We want audience also to be active and engaged in our webinars. Therefore, in the panel discussion, we encourage all of you to participate in the discussion and raise your questions and discuss your ideas. You don't need to take notes. All webinars are recorded and we make the video available to you afterwards. So if you do not want to have your picture recorded in the videos, please turn off your camera during the presentation. But we will not share we will not record the panel discussion. So during the panel discussion, you're more than welcome to turn on your camera. So it's easier to communicate and contribute to the discussion. For those who are not familiar with Zoom, the basic functions you can find at the bottom or at top of the Zoom presentation mode that you see right now. On the very left side, you see the function to mute or unmute your microphone, as well as turning on or off your camera. And there's a chat function that you can use for raising your questions. You can raise your questions either to me or my colleague Madeline, or just very commonly raise your questions to everyone. And as I said, we will try to answer all questions after the presentations. Before we move to the main presentations, I would like to give you an overview of the activities that we are doing as alloy development at Jönköping University. We have received, a few years ago, we received a strategic fund from Jönköping Foundation, who is governing the Jönköping University, to develop strategic alloy development activities, a project called STRAIGHT, and looking at different aspects of alloy development, especially for metallic materials, including advanced alloy design, including different processing for material processing, for example, coating and surface technology, metal casting and wrought alloys and 3D printing and other techniques as well. And under the umbrella of this strategic fund, we have been successful to receive external funding from different funding agencies. Of course, together with, as a collaboration with our industrial partners, that you will see them in the next slide. So you will see a summary of the projects in this slide that we are running. We had, for example, a light project, which was a feasibility study together with our industrial partners. We were looking to see how can we improve the thermal stability of nickel-based alloys based on the high entropy concept. So not to produce high entropy alloys, but how to use the concept of high entropy alloys to develop the performance of existing alloys, which was a successful project, and it continued and became a full-scale project, looking into more details of the concept that I mentioned, using high entropy alloys to develop the performance of super alloys or nickel-based alloys. The project is still running together with our industrial partners. Similar concept we have been applying also on lightweight materials to see how we can apply the high entropy concept on lightweight alloys to modify them in order to improve their performance, especially at high temperature. But with lightweight, we're talking about mainly aluminum and titanium alloys. The Novella project was also a feasibility study project, and after that, we, together with our industrial partners, we agreed to continue the project, and it's a project that is running right now, and the principal investigator is Patrick, who is also presenting today. Again, looking into details of how can we use the high entropy concept to develop the lightweight alloys. In addition to that, we are also trying to use the same concept for development of iron-based alloys, as well as looking different applications. For example, we have another project running right now, all for hydro, that is looking again on iron-based alloys for hydrogen applications. For example, automotives that are using hydrogen as a fuel, how to design a material that is resistant to hydrogen at high temperature as well, using the high entropy concept or any advanced alloy design strategies. We are looking also on other processing techniques. It's a project that is running by my other colleague, Katerina Zanella, who's looking on the novel processing for high entropy coatings that is running again at Jönköping University in an efficient and cost-efficient manner. Together with our colleagues in Germany and Poland, we are also we have applied for a project that in that project we're also looking at other applications of metallic materials in biomedical applications. How can we develop alloys for biomedical applications? I forgot to mention in the slide that the principal investigator for this project is my colleague Jörg from Fraunhofer Institute in Germany, and we are partner in this project. We are happy to be the partner in this project as well. Hopefully it gets granted soon. Other projects that are also on the pipeline, we are looking to see how can we combine 3D printing and metal casting in order to develop alloys for materials that are sort of, we can say, medium to high entropy composite structure with designed or architected structure. That is also a project, a proposal that is under review. If you need to know more about these projects and if you're interested to collaborate in related topics, you're more than welcome to contact us and we'll be happy to discuss that. As I mentioned, we could not do all these research and progresses without our industrial partners. In this slide, you see the main industrial partners that we have in the projects that I mentioned, at least the active ones. And we are very honored to work together with all our partners, both industrial partners as well as academic partners in Sweden and also internationally. In addition to what I mentioned so far, there is also another big activity going on. There was a European scale project that we submitted this year. The result will come during spring 2022. And it was a very intensive work to develop a project about high entropy alloys for harsh environments. We are looking at application of high entropy alloys for different environments, for example, corrosion or high temperature, high mechanical pressures and so on, loads and so on. And it's a doctoral network. We will have hopefully 10 PhD students working on this topic for 3 years. And as you see, we have around 18 partners in this project. Jönköping University will be hopefully the coordinator. When I say hopefully, it means that hopefully if we get the fund. And we have a nice combination of universities, companies, and research institutes in this project that we are very looking forward to hopefully get the fund and start working on. It was just to give you an overview of what we are doing, the research activities that are going on right now. There are of course a lot more, but just to give you an idea of what we are doing. One of the main activities that we have been developing, and Patrick has been the main part of it, is high throughput screening. How can we develop methods for accelerating the alloy design for high entropy alloys? And I welcome Patrick to start his presentation. Very much looking forward to it. So Patrick, please.
Thank you, Hassan, for the introduction. As Hassan said, I'm going to be talking about our current work on high throughput screening, particularly focused on industrial applications. If you want more information on our work at the moment, you can probably find a lot of the information I'll present today in our recent publication, and you can see the link for that below. As a quick overview, I'm going to very briefly cover a history of alloy development, just so we can see previous large steps and where the trends are going. I will talk about a very brief introduction about high entropy alloys, just so we're all on the same page. And then the main part of the presentation in the high throughput screening techniques and a couple of case studies that we have done here at Jönköping University before a quick summary and future outlook. So having a quick look at the brief history of metals and alloys, I want to identify some of the big forward steps that occurred in alloy development and physical metallurgy, and try and identify where we can go from here in the future. Metals and alloys have been used for centuries and dates back even before the Bronze Age to where people were just using precious metals, golds and silvers. But the Bronze Age and subsequently the Iron Age is where we really started using metals and alloys for tools and weapons. It wasn't until the 1700s that we first had an understanding of quench hardening in an iron carbon system. And then later in the 1800s where we started developing steels for uses. The iron carbon system, it wasn't even until 1896 where the first binary phase diagram was drawn up by Robert Austin, and this has obviously since been significantly improved with much more detail over wider composition. One of the early developments not directly to do with alloy development was the discovery of X-rays around the 1900s, which really rapidly increased the research into alloy development and increased our understanding of how alloys deform and etc. A few early step forwards in alloy development was H. Harding by Wilms in 1906, and subsequently followed by the discovery of martensitic steels by Brearley, who was looking for a more corrosion resistant steel. Nickel-based superalloys was then discovered with the use of gamma prime particles for elevated temperature applications, but the gamma prime wasn't actually seen until the 1950s, where we had electron microscopy and we could observe the gamma prime particles to actually understand why these alloys have such good thermal properties. The 1950s and 60s then became a bit of a hotspot where we started to understand dislocation mechanisms. And this was from a lot more than just these guys: Irwin, Fleischer, Labouche, some common names, also Mott, Cottrell, all big names in terms of understanding how dislocations moves, seeing dislocations, and putting forward models such as solid solution hardening, precipitation hardening, so that we can start tailoring our alloys a bit more towards mechanical properties. More recently, a few of the more recent alloy discoveries have been metallic glasses in the late 60s, with much more work from the 70s and onwards. And then when we come to steels, a big breakthrough in the strength ductility barrier, which has always been a challenge, has been with TRIP and TWIP steels in the early 60s, and then much more recently for the TWIP in 1998. The most recent alloy development, or the most recent discovery in terms of alloy development, was the introduction of high entropy alloys by Cantor and Yi in 2004, which in the previous 10 years has gained a lot of traction, as really taken off as an interest for potential future alloy development. Currently though, most alloys are tailored to try and maximize the mechanical properties and thermal properties by a series of mechanisms such as precipitation hardening, solid solution hardening, martensitic strengthening, things that we've known since the 50s. And these are ways of, I guess, controlling dislocation movements to improve the mechanical properties to some very specific applications. However, this has meant that since the 50s, 60s, where we had large step forwards in mechanical properties and thermal properties, these mechanisms have allowed us to tailor the properties to very specific applications, but it's giving us smaller and smaller reward for the input of work we're doing. We gain smaller increases in mechanical properties for the current research. And this is where we hope to use high entropy alloys. As I said, it was introduced in 2004, and this was by Cantor and Yi. And the original definition for this was alloy containing at least 5 principal elements between 5 and 35 atomic percent solution, and it produces single or multi-phase solid solution. Why it was called high entropy alloys is that because if we mix more elements in an equiatomic constitution, we increase the configurational entropy. This is important because if you look at where the entropy sits in the overall Gibbs free energy, by increasing the entropy, we decrease the overall Gibbs free energy of this system, and a lower Gibbs free energy means a more stable system. The additional little bonus for this is the fact that the entropy is a magnitude of is a multiple, of the temperature. So if we had high temperatures, we even further increase the entropy of mixing, which gives us a lower Gibbs free energy again. The benefit for this sort of approach for alloy development is that instead of looking in the corners of binary, ternary, or higher order systems with one principal element, we've opened up the compositional region for exploration significantly. We've got a huge new area of composition that we can actually start looking for new alloy systems. And the mechanism behind, or the result of mixing all these elements together can sort of be seen in this schematic, is if we substitute a pure, in this example, chrome-based lattice, with more and more elements, we get a large amount of distortion of the lattice. And this can lead to some very interesting properties. But that's not quite the only way we can mix our alloys together. This was quite a nice presentation of the different ways we can mix alloys together in a Nature Review paper by Isa George. And he showed this nice example where if we take, for example, a ternary system, we can mix our 3 elements and we can get our single solid solution, which is what we typically talk about in high entropy alloys. We can also have a spinodal decomposition. This has been seen in a lot of aluminium, titanium based HEAs. We can have multiple solid solutions, so different compositions all having very equal driving forces of free energy, or we can have what is probably more commonly seen with current alloys, with a solid solution mixed with a intermetallic of a highly ordered structure. Again, what all these sorts of different mixing of elements can give us is some very unique properties for high entropy alloys, which it's often reported to have an increase in both tensile strength and elongation, along with improved cryogenic temperatures and other very interesting properties. So high entropy alloys is definitely something that we should be looking for the next big step forwards in alloy development. However, there is a big challenge with high entropy alloys. With opening up this compositional space, it gives us a huge number of potential alloys that we can start investigating. And this is, quite frankly, just experimentally and computationally a huge challenge. We can't look at all of these compositions together, because if, for example, we just take a 5-element system and look at 1 atomic percent step of each constituent element, we end up with a million compositions. And basically, as you can imagine, that's not feasible to produce that many compositions. This is a figure of the periodic table from a review in 2016 showing all the current, well, at that time, unique high entropy alloys. And you can see we have a lot of high entropy alloys produced within the ternary metals. And this sort of gives you an idea of how many different combinations that we can actually make with this new technique. So how we are trying to approach this problem at Jönköping University is through a method of high throughput screening. And this is computational high throughput screening, which is trying to aid our experimental approach. What we want to start by doing is identifying compositional regions of interest based upon the phase or phases that we expect to be there, along with other potential attributes such as cost and density, which are quite easy to calculate, but also adding some sort of mechanical models to it, looking at solid solution strengthening or stacking fault energy, for example, to try and predict how the alloys will perform. And the way we do this is by using the Calfad approach, and we use this in collaboration with Thermocalc software. Thermocalc has been a long-time partner of us at Jönköping University, and it really supported us with our high throughput screening processes. The way Thermocalc works, for those who may not know, is it's the calculation of phase diagrams, which is what Calfad stands for. It takes experimental data from binary and ternary systems to calculate the Gibbs free energy as a function of the composition, the temperature, and the pressure. From the free energy curves for each individual phase, you can then calculate a phase diagram. If you combine multiple binaries and ternaries together, you can predict phase diagrams for systems that we haven't investigated for with pretty good accuracy. And Thermocalc is always improving their databases, and we've seen some quite significant improvements from each HEA database with our simulations and experimental results so far. From once we are able to use the Thermocalc software, we want to start screening the compositional space for what we are going to call, and what I'll refer to as, islands of interest. And these islands of interest exist in multi-dimensional space. It's something that we can't easily visualize, so we need some software to help us pull this out. And the way we do this is we start with a Python code, which writes all the potential compositions combinations of compositions based on our inputs. These inputs are typically based on empirical data and literature studies, so that we know what is likely to be soluble within binary pairs. We can then set our temperature limits to see which temperature scales we want to be looking at. We call upon thermocalc to run all these calculations. We then extract the data of interest. For us, this is typically the phases and sublattice compositions, and then we create a database. The efficiency of our code at the moment is that we are running on a multi-core computer specifically dedicated just for our high throughput screening, and we can get through about 1 million compositions in approximately 3 days. This obviously depends on how many temperature steps we are looking at. The next challenge of high throughput screening is data processing and visualization. So as I said, we want to try to extract where these compositional islands are of interest so that we can start our experimental investigation from some specific point. To do this, we do need some background information on what phases we expect or what phases we would like to be looking at for the mechanical properties. This can be something as simple as just we want single phase FCC. From then, we then apply a k-means function to try to locate the center of the islands. This is a fairly rough drawing of what an island may look like in multi-dimensional space. And the reason why we hit the center as our first experimental point is that, for example, if we go on towards the edge, when we actually produce experimentally, there's always a slight shift in alpha adverse experimental results. So to make sure that we are actually producing what we think we should, we try to hit the center of the island, and then from there, we can then move in a direction that we think is favorable experimentally. When it comes to visualization of the data from our high throughput screening, this is relatively easy for 3 component systems. That's our standard ternary alloy. 4 component systems, we can even plot in a quaternary diagram, which we have now modeled, and we can pull out where all phases sit within the quaternary system. But this starts to become a significant challenge for 5+ component systems that is starting to look in multi-dimensional space. What we do is we start to look at binary maps, and this is basically just to highlight the regions of interest for us. Each temperature you can see within this curve is, so each color you can see within these plots is highlighting a temperature, blue being low temperature up to red being high temperature. This is for a fairly standard iron, cobalt, chrome, manganese, nickel, high entropy alloy system. And I will talk a bit more about this in that case study shortly. The black line, or the worms as I call them, is identifying the center of this compositional island with increasing temperature. But we have to be careful with this sort of visualization, and that's because we're just looking in binary system, and points from ternary or quaternary systems can often skew the visualization of this a little bit. So we have to be careful when we are interpreting these results. What we can do from here, though, is take a slice at any temperature and identify the center of the composition. And we can look at that for different temperature steps to see where our center of ideal composition or ideal phases lies. As I said, we can apply this to single or multiple phases, and we can also apply this to the percentage of the second phase if you would like. But as you know, phases don't tell us everything, and we want to know, once we hit the center of a compositional island, which direction we want to be moving in. And that can be based on some more simple models. As I said before, density and cost are very easy to model, but we can also apply some more complex models such as solid solution hardening or stacking fault energy to try to tailor the mechanical property to something that we want, whether it's increased formability, increased strength, greater formation of twinning. So we apply these additional models to try to tailor our microstructure to what we actually want to achieve. And this is where I'm going to jump into my first case study. And this is on an iron-based high entropy alloy where we were trying to reduce the cost of currents high entropy alloys. One of the major limitations of high entropy alloys at the moment is the cost, because if you try to put equiatomic elements of all our equiatomic composition of all our elements, which then means we have to have, for example, 20% plus of cobalt and nickel, which are very expensive items. So what we did was we looked at the very well-studied iron, cobalt, chrome, manganese, nickel system, and we set limits on the amount of expensive cobalt and nickel that we used, cobalt to 10% and nickel to 20%, and performed a high throughput screening and identified a compositional island, the center of a compositional island at this composition here, iron rich at 43%. And this composition was 40% cheaper than the equiatomic alloy, but we also found that we had improved work hardening and improved thermal strength. And when we did in situ studies on this alloy, we found that we had managed to activate twinning, and that's because we had reduced the stacking fault energy. So in order to take the study a little bit further, we wanted to try to predict the mechanical behavior. So we applied a solid solution hardening model, which we have adapted from a typical Labouche style solid solution model to fit high entropy alloys. And that adaptation has come into the modulus and misfit parameters. You can see more about that in that paper, or I can describe a bit more about that in the panel discussion afterwards to try to identify the direction you want to move for future alloys. We also looked at the stacking fault energy, and we applied a thermodynamic model where we first need to calculate the Gibbs free energy of the HEP and FCC phases from thermocalc, and then we can put into this sort of semi-empirical formula and calculate the stacking fault energy across the whole system. Where we had originally produced our alloy, you can see here in the iron-rich corner, and using these models, we found that the maximum solid solution hardening was towards the nickel chrome side, and the maximum stacking fault, sorry, the minimum stacking fault energy, we need to reduce the stacking fault energy to initiate twinning, was down towards the iron-rich corner as well. From this, we have suggested a number of future alloys, which we will try to be producing shortly, based on either maximizing solid solution hardening, minimizing stacking fault energy, or a combination of the two of them to try to optimize the mechanical properties while reducing the cost even further from what we have produced in the first study. So this is one of the ways that we're tackling the high cost of high entropy alloys to try to bring it closer towards industrial realization. The next case study I want to do is a more industrial based one. And as I briefly mentioned this project in the introduction, and this project is called Novella. Novella 2 is the one that's currently running and is supported by KKS. And it came about from our partners at GKN. We wanted to replace a current aluminium silicon cast alloy in the jet engine, because what they're using at the moment, they would like to improve the thermal stability slightly. However, the next alloys available to them, with being titanium, even though it easily performs to the task, it's more than what they need, it's over-engineered and it's too expensive. So what our task in this project is to apply the high throughput screening concept and the high entropy alloy concept to try and fill this void between aluminium alloys and titanium alloys in this green region of what I've called compositionally complex aluminium alloys. We have targeted a density between 357, a 70% cast silicon alloy, and Ti 6.4, which is what they were thinking as the next best solution. We also want to be able to maintain a comparative specific strength to what they're currently using, or improve on this, and still maintain a thermal strength and stability at 200 degrees. Our other partners in the feasibility project was Husqvarna, because they can use any sort of lighter weight, higher specific strength material in the handheld components, and thermocalc, as they've always been supporting us a long time and giving us access to the software to actually run these high throughput screenings. We approached this project by taking a look at 3 different approaches, one coming from the aluminium-based alloys, so starting with the aluminium silicon alloy, testing the solubility limits and trying to produce an alloy with relatively low density, We came at this from the opposite direction of titanium-based alloys from a Ti-6-4. This gave us a lot more freedom actually, because alpha beta titanium has a lot more solid solubility than aluminium silicon does, and tried to produce something a little bit cheaper and lighter compared to Ti-6-4. And then we also came at this from a strictly fundamental high entropy alloy composition and complex alloy approach. I'm going to talk first about the aluminium-based alloys that we've looked at. I saw we had a few in the attendee list who were interested in the development of aluminium alloys. So we started by looking at just the periodic table, taking the elements that are likely to be soluble with aluminium silicon, also a few elements in literature which suggest that could be interesting property-wise, and also we grabbed some additional lightweight elements. Performing some high throughput screening just on the solubility of these elements within a aluminium 7 silicon system, we found that our best solubility was coming from these 4 elements here: copper, silver, zinc, gallium. Gallium we decided not to continue with because of the low melting point, but we also have solubility of up to about 0.7% magnesium. So what we decided to investigate was the combination of magnesium, silver, copper, and zinc. We did our high throughput screening with combination of all these alloys and came up with a series of compositions. I will show you the tensile results in the next slide. But what we found was that we are always producing, as we expected from thermocalc, a single phase matrix with only the silicon precipitates present. If you can compare this to a typical 357, where we typically have some sort of iron intermetallic particles. We then try to take the further step forward, apply some of our solid solution hardening models to this high throughput screening. And you can see that magnesium is certainly the most potent solid solution strengthener within the system. However, when we plot this just within the single phase region, we can dissolve quite a bit of magnesium in the aluminium system. However, we can't get much of anything else in there at the same time. And what we found was that actually by increasing silver, even though it is the weakest in terms of solid solution hardening, it gives us increased solubility of zinc, magnesium, and also copper, which is not modeled here. And that led us to the development of these 6 current alloys. We have another 4 that are being produced, and we have shown some very promising results so far at both room temperature and elevated temperature. The tensile curve you can see here, the black curve here is the reference 357 alloy, which has a yield strength of about 250. I think it's actually about 248. And through tailoring the solid solution hardening effects, we have managed to increase the strength quite significantly at room temperature. And also if we are clever without the formation of precipitates, we can significantly increase the formability of these alloys. The next step of this project is to then try to introduce precipitation hardening as well, which will sacrifice a little bit of the formability of some of our best performing alloys, but we can further increase the strength and hone in and tailor the final mechanical properties as our partners sort of would like to see them. Coming back to the second approach we looked at, titanium-based alloys, I'm going to show you some of the first screenings we did looking at an alpha beta titanium system. And as I said, we actually have a bit more room of freedom with the elements we'll select with alpha beta titanium alloys. We have a bit more solubility. And what we want to be looking at is identifying regions at 1000 Kelvin, which have about 4 to 8 volume% beta. And from literature, this is where we sort of get a optimum ratio of strength and ductility. And when we took this approach, we found the center of compositional islands with about 4 to 8% beta sitting at this titanium 76 aluminium 10% ratio. We have produced a couple of the alloys from the study, and so far we've only got hardness results and they are looking extremely promising. We still have to produce tensile samples to confirmed that we have good formability with it as well. But the next step was to also try to reduce the cost and density of this alloy so that we sit between the 357 and Ti-6-4 region. And we've done this by trying to maximize the amount of aluminium we have within the system. And we found two regions based on having constitution of vanadium zirconium or vanadium zirconium, hafnium, and niobium. So this is one of the ways we're approaching titanium alloys to try to improve or decrease the cost and density while still hopefully maintaining the strength and ductility and thermal stability that Ti-6 is known for. Just quickly, a couple of further alloy development projects that we have going on. As Esan also talked about, one of them is called All for Hydro. We're applying the high throughput screening technique to this, looking at the phase evolution to try to identify compositions for hydrogen resistant material. And the second one is applying the high entropy concept to nickel-based superalloys. And finally, a quick summary of what I've talked about is that we are seeing very promising results from our caliphate and high throughput screening in identifying these compositional regions of interest. And if we further couple this with some physical empirical models, it is really helping us guide our experimental investigation to find alloys of real interest mechanically wise and tailoring these mechanical properties to very specific requirements that we see a need for within industrial applications. The future outlook for high throughput screening is to try to apply further models so that we can enhance a prediction of mechanical properties even further. And that can be from grain size refinements and ICME models applied to high throughput screening. Finally, after high throughput screening, computational, it's also nice if we could come up with methods for experimental high throughput screening. Thank you for the time and attention of this presentation. But before I go and pass on to Jesper, I would like to thank all of our partners that have been involved in this project. As you can imagine, it doesn't happen just with us at Jönköping. We have a lot of industrial partners who have been with us for quite a while in various projects, a few universities who have helped us with experimental investigation and sample production, and also our funding agencies who have very kindly supported our projects along the way. And with that, I would like to thank you, and I would like to pass on to Jesper, who will talk a bit more about actual material sections in jet engines.
Thank you very much, Patrick. Before we move to Jesper presentation, I would like to know if there's any question from the chat. I think there's just one just came. It's quite a long
one.
question, but I can read it to you so everybody else can also hear that. Speaking of aluminium, I mainly deal with 3000 discs, 3000 alloys and 6000 alloys at IKEA, company in Sweden. We are always about affordability and obviously for basic applications. In casting sector, we have looked into replacing zinc with recycled aluminum and magnesium casting, so lower density and cheaper in volume rather than kilogram. However, the challenge we are facing for discs and profiles are, first of all, tremendous price increase over the past 1 or 2 years. And the second, aluminum prices depends on the stock market, meaning the same grade could be cheaper in China or more expensive in India. Is there a way to lower aluminum alloys prices by making new alloys or making existing ones cheaper? That is a financial question.
That's a very financial question. And we've been trying to get a project off the ground with steel alloys to reduce the cost of steels through recycled materials. And in that project, we're trying to look at what materials we can cheaply recycle, perform our high throughput screening based on those elements, and then seeing if we can come up with a composition from solely recycled materials to try to decrease the overall price. And I don't see why we can't apply a similar process to aluminium alloys. especially now that we have a bit of a background with silicon cast alloys. However, I'm not fully up to scratch with the stock market prices for aluminium in different countries. So I can't answer straight away if that's going to make it significantly cheaper or not. But we can certainly look at just taking, for example, a recycled material into aluminium production to see if we can get at least similar mechanical properties to what you currently have with your 3000 and 6000 alloys.
Sure, thanks. I can add to that also that since I'm involved in another project with another colleague at the department, we are working on using the scrap aluminum materials that we have from cast components and recycle them and improve the quality for wrought alloys. So producing wrought aluminum from recycled cast aluminum. And the main application is normally automotive or some household applications. So looking at recycling the alloys from casting, bringing it to wrought alloys and such could be one way to at least reduce the sustainability or improve the sustainability aspects in production of metallic materials. That, as Patrick said, can be applied in other systems as well, as we are looking for steel, for example. And in that project that I just mentioned, we are extending that project to a full-scale project. And if we get funding, we are actually looking into implementing this high throughput technique into conventional alloys as well, not only high entropy alloys per se. So I hope we answered your question. If there's more to discuss, of course, we will be happy to discuss after the webinar as well. The next question is from Jitin. Very excellent talk. I would like to discuss on compositions obtained after alloy design, whether the compositions obey INOE rules, for example, titanium 72, aluminum 12, blah, blah, blah. Here, titanium is 72%, whether it will fall within high entropy alloy range or not. So is it a high entropy alloy per definition or not?
So yeah, these will not fall into the traditional definition of high entropy alloys of greater than 1.5 R. To get that, you have to have almost equiatomic at a 5-element system. What we're doing here is basically trying to apply the high entropy concept to more traditional alloys, increase the entropy a little bit, see if we can increase the solid solubility and the thermal stability from there. So they're not within high entropy alloys, but they're moving towards these compositionally complex alloys or multi-principal element alloys. Yeah, so I hope that answers the question.
Thank you. The next question is from Nele. Thanks for interesting talk. How many alloys are roughly being tested experimentally after the first screening step by CALFAT? And how many iterations are needed to come to a final solution?
That's an excellent question. And it very much depends on the system and sort of how big the compositional space was to start off with. Actually, for the Novella project, our first alloy that we produced in the silicon range, we had a 30% increase in strength and still a 5 to 10% increase in ductility on the very first alloy. So we can, if we're lucky, get something from the get-go. From there, we've further developed it with another 6 alloys. The steel one that I presented, that was also the first composition from there, but again, with more improvement based on the experimental direction after that, based on those first results. So yeah, it really depends on which system we're looking at.
Exactly, and to add to that, it's a dynamic process. These codes can be continuously developed as we are doing right now as well. So you just saw the primary results of this technique, and this iteration is always needed to always improve the algorithms for modeling and bring it closer to the experimental reality.
Yeah, and as you can imagine, models are never perfect, so it's never going to be exactly what you predict computationally.
Absolutely. It's just to narrow down the experimental work. The next question is from Jörg, asking, what about intermetallic phases if you put so much aluminum and titanium?
Yes, the TiAl3 phase. Yes, that's getting very close to the boundary of where we're looking. We can model down to low temperatures as well to see exactly when it will form. It seems we have suppressed it a little bit with the extra elements we put in, but it's definitely something we have to be careful of. So far, we haven't produced any ALTI3 phase in our alloys that we produced so far. But yeah, no, we're definitely on the boundary of it. And yeah, we're trying to see how far we can push that boundary away and how much we can suppress the intermetallic phases.
Great. Thank you very much. Very interesting questions. We hope that we
Yes.
answered at least a little bit your questions. As you know, there is a panel discussion after presentation by Jesper. So you're more than welcome to continue your questions or raise new questions in the panel discussion. And now we have Jesper with another interesting talk about material development. And Jesper is going to present to us what is the application of these alloy developments in industry, especially in aerospace. So Jesper, the scene is yours.
Thank you. Yes, and I would like to start with thanking Patrick for a great talk here. It's really interesting to listen to all the details. Yes, so first off, I will try to quickly describe how a jet engine works, if all of you don't know that. And the main thing is that we have two main parts of a jet engine. We have the bypass air, where most of the air passes through the engine. And then we have the core of the engine, also where we generate power. And usually when we try to describe how a jet engine works, we can simplify it with 4 words. So we first try to suck the air in the fan, and then we squeeze the air in the compressor stages, and then we bang the air in the compressor, and then we blow it in the turbine. So suck, squeeze, bang, blow. It's really simple. And when we want to increase the efficiency of a jet engine like this, we want to increase the amount we compress the air with in the compressor, so that when we ignite it in the compressor, we get out more power of the air. And when we do this, the temperatures, they increase also in the turbines and in the compressors. So really, when we want to increase the efficiency of a jet engine, the air in the jet engine will become hotter. And to account for that, we need to develop alloys that are more thermally stable, that can handle these increased temperatures. And now I will really simplified try to mention which types of material types we have in a jet engine. So in the bypass air, we can have composites, because here it's cold. And then in the front part of the engine in general, we have titanium alloys, but also aluminum alloys. And in the aft part of the engine, we have nickel-based superalloys generally. So at least when I think about design of materials, I see it in kind of 2 ways, or maybe 3, and Patrick has talked about the third one being how we can design new alloys. But the main part, or one of the main parts for me, is how we can tailor material properties for existing alloys based on heat treatment, design, and processing of the material. And then another important aspect is the alloy selection, and knowing which alloys we should select for the next generation components that we are wanting to produce. And here, especially if we are increasing temperatures in the engine and we don't know, our comfort alloys, if we call it that, aren't thermally stable anymore, then we need to find new appropriate alloys in these areas, and we can't test every one of them. So then we have to probe which alloys we think are the most promising ones and test those. So talking about how do we think about tailoring material properties, really. First, or a main part of the work that we are doing at GKN at the moment is working with additive and trying to develop additive processes where we can shorten the lead time and decrease the buy-to-fly ratio. And the buy-to-fly ratio is the, if we buy a forging and then we need to machine away a lot of the material to get the final product, all the machined away part, we want to minimize that one. So for additive especially, but generally also, we need to develop process parameters that are of the correct quality, so that we get good amount of penetration and stuff in the beads when we build them, and then when we build the next one next to them as well. As well as we need to make sure that we have a good microstructure in these parts when we are done with the heat treatment. And finally, the material properties need to be really what we desire in the part. So instead of doing this experimentally, we want to be able to do this virtually in the computer instead. And here we have developed tools to be able to predict the bead and how the process behaves firstly then in the additive to get a thermal history from that one, and to be able to assess the process parameters feasibility for production. And then we want to be able to use these thermal histories to predict the microstructure and all the important phases that comes with that and features. And finally, we want to use this to predict the material properties in the end. And as Patrick mentioned, we have lots of different parts that feed into the material properties. So here are a few of them, and at the moment, the aim that I am working with is to be able to predict the yield strength based on for a given alloy and a given microstructure. And when we want to do this, we have identified these three areas at the most important ones at the moment. There probably are more. And why have we chosen, or why haven't we chosen the other two here? If we talk about the phonon electron drag, that one is triggered at really high strain rates. And generally, when we want to assess alloys, we look at low to semi-low strain rates. So we don't have to care about this one for regular yield strength predictions. Tailor hardening, why aren't we looking at that? Yeah, the Tailor hardening part really is the work hardening of the material. So, and that would trigger after yield strength mainly. So we have chosen to not include that also in the model at the moment. Of course, both of these will probably be included at a later date. So then what is solid solution strengthening? Patrick mentioned a little bit about this also, but it really is how it's triggered by the misfit of the different alloying elements in the alloys and the different sizes and stiffnesses that they have contribute to the increased strengthening of in the solid solution. And here we are using similar models to what Patrick talked about. And then when we talk about precipitate strengthening instead, we see that, or we know that the precipitate sizes and their volume fraction have a huge impact on the strength of the materials. So, and then we have implemented a few models for that as well, to trying to understand how the precipitates affect the strength of the alloy. And then finally, if we look at these and evaluate how good are these models then that we have, for them at the moment, for one of the first predictions we have done, we see that we have a rather good agreement with test data. So the blue line is test data, and then we see the model predictions. However, if this is a general, if we were lucky this time, or if this really is how good the models are, more development will have to show. Yes, and so then how can we use these tools then? And one of the main things that we can do is to use these for material selection for new components. And to be able to use tools like this for material selection, first we need to know what does the product really require. And these requirements can vary throughout a component. In some areas, we maybe need to have a strong and ductile material, while in other areas, we need to have a creep resistant material, because the conditions will vary over the part. So it's really important to understand the product requirements here. And then once we have done that, we want to apply our understanding for how the contributions affect the material properties and the producibility also of the concepts. What really do we look at when we do this? Strength is one of the key stuff that is important, and crackability or lack of crackability is also an important aspect. And then when we talk about cracks, we can have different types of cracks that come up in different areas during production. So sometimes some cracks are created during solidifications, while others are created during heat treatment. And these are triggered by different stuff. So we need to understand what affects these cracks so that we can screen away these alloys also at early stages, because it's not acceptable to produce parts that have defects in them in the aerospace industry. Yes, and with that, I would like to thank you for listening.